Okay, the next topic is deterministic complexity classes. So up until this point, we were only concerned to answer the question, what is computable, what is not? So what is an algorithm and what is not? So basically this is the same question. But now we shift our attention to the question, okay, computable under what resources? So now we also pay attention to the resources that we're using when we're computing something. And the resources are of three types, basically. It's time, how much time does it take? How much space does it take? So for us, it will be how many cells is my Turing machine visiting, basically. And the determinism and non-determinism. So if we use, as you remember, when we did an NFA, non-deterministic finite automata, it was able to follow many routes at the same time. So this is also a resource. It's like okay, whatever. And we will define complexity classes. This will be basically a set of languages which are, so the complexity class R will be some set of languages which are decidable by a Turing machine in some bound resource. So let's say in some time or in using just only some space and so on. And the most famous classes in computer science and also very famous in mathematics is P and NP. P will be languages. It's the class of all languages or problems, you can think about it this way also, that are decidable in polynomial time, O and K. And NP will be languages decidable by a non-deterministic Turing machine in a polynomial time. And the most famous question in computer science for sure is, does P equal NP or not? That means if the language is decidable by non-deterministic Turing machine polynomial time, can I decide it by deterministic Turing machine polynomial time? So these are the questions that we will try to address. This is the nature of questions we'll try to address. And so we recall some definitions which we already gave, but this is our bread and butter, and let's recall them now. So now let's say I have a language L, so collection of strings over some alphabet A, and I have a Turing machine M. And now I have two functions from natural numbers into real numbers. So they take natural arguments and they can produce positive real numbers. And I want to use them as resource bounds, basically. So I'll call one function S of n for space, and the other function I'll call T of n. And they're supposed to measure time and space, right? So as we are only interested in machines that read the whole input, I think of a Turing machine, let's say, that reads input of length n, then it has to make n steps. So if my machine reads input of length n, it must make n steps, and it must visit n cells. So I will always assume that S of n is bigger than n, the number of steps my machine is taking, number of space my machine is occupying, meaning number of cells it's visiting, is always bigger than n, and also T of n is also always bigger than n. But you can also do other things. We'll mention it when we get to it. Let me remind you of a very important definition of accepting. Turing machine M accepts L, language L, if and only if for any string in A, so in A star, so for any string, if I start my machine on this string, this machine holds in an accepting state if and only if this word is in L. So what I'm going to do now, we are going to modify our Turing machine so it's easier to handle. We're going to add reject states. So before I only had accept states, and I also told you that I might make a definition so that when it enters an accept state, it has no way forward. So it gets stuck in accept state. So it only holds in accept state. In all the other states, it continuously loops. But now I will add reject states, and then M accepts L will be, if given W, it holds in an accepting state if W is in L, and if W is not in L, it might not halt by entering a reject state, or it might loop forever. But for now, we haven't defined it yet. So it's accepts means that for all strings, it holds in an accepting state if and only if the string is in L. But there is no condition in some sense. If a string is not in L, it does not hold somehow. But when I add reject states, you will see that if string is not in L, either it might halt in a rejecting state, like here, or not halt. So there would be two different things for not halting. And then there's another way, another definition, important one, that M decides L if it tells you yes and no, basically. So there's a condition, if your string is not in L, it also tells you 0 somehow. It computes this function high L. So for every string, it has an answer. In accept case, it only basically has an answer if the string is in the language. And we saw many examples, and we also saw how very different these two things are from each other, philosophically also. Okay, so I reminded you about this definition, and now we also mention this definition before, but let's do it again. The Turing machine M is Tn time bounded, so Tn is a function, so it can be like, let's give an example. So I don't know, just like say Tn is 1 by 1. Let's say 2n squared. So it's just some function that maps n to 2n squared. And M is a Tn time bounded if for all strings, if your string has size n, then machine M started with W halts after at most Tn steps. So let's say if I give it an input 0, 0, 1, 1, then the length of this input is 4, and 2 times 4 squared is 32. So if your machine is Tn time bounded, it doesn't make more than 32 steps when you give it this input. And it has to follow with this for all inputs, basically. So first of all, you notice that if the machine is time-bounded, it has to halt, right? The time-bounded machine always halts. This is number one takeaway. Now, a space-bounded machine, so let's say now I have maybe the same thing again. Let's say Sn is also the same function, just for simplicity. So now M is an Sn space-bounded machine if again for input the number of tape cells visited by the head or occupied by the input is at most n. So again, if my input is the same, the space-bounded machine says that it's 32, so 2 times 4 squared, this is Sn, S4 in my case, it's like this. Right, S4 is like this. So it doesn't take more than 32, doesn't occupy more than 32 cells, but it doesn't mean it halts, because it might continue looping inside 32 cells. Okay, so it might go back and forth, back and forth, back and forth. But if I set it not making more than 32 steps, then it has to halt after 32 movements. But somehow 32 cells doesn't give it a bound on how many steps it's making. Okay, so you might even have just only 2 cells as your bound, but your machine might go back and forth forever and might never halt. So Sn space-bound machines do not necessarily halt, whereas time-bounded machines halt by definitions. And let me remind you one another definition. A complement of the language is everything outside this language. Okay, let's make our definitions so that the promised definitions deciding by end state. So we'll modify our Turing machines now, and now they will also have a reject state now. So my alternative definition of a Turing machine is that I have set of states, alphabet symbols, transition functions, start state, everything the same, and then I have accepting state and I have rejecting states. So I have ZA for accepting states, ZR for rejecting states, and I assume that they're not the same. I mean, you cannot have a state with accepting and rejecting. We bend this. So accepting states and rejecting states are very different. And we will say that M decides L by state. I mean, we will show that these two things are exactly, this is an exercise, but for now, let's use a different terminology. M decides L by state if for all W, machine M started with W holds in an accepting state if W is in L, and in a rejecting state if W is not in L. So your answer yes and no, that was 1 and 0, computing 1 and 0 before, now it just goes to an accepting state or goes to a rejecting state. So if your language is decidable, a machine will exist that goes to an accepting state or rejecting state. Okay, so now you can see that there are three possibilities that your machine can do. Either it goes to an accepting state, it goes to a rejecting state, or it loops. And there are now two very easy exercises which I will ask now, and I want you to solve it. That let's say L is decided by Tn time-bounded K-tape Turing machine in the old definition. So I know that the language is decided by time-bounded K-tape machine. Then language is decided by a Tn plus some constant time-bounded by state. It's decided by state by Tn plus some constant time-bounded Turing machine. So according to a new definition. If it's decided by a K-tape machine according to the old definition, then it's decided by a K-tape machine according to the new definition. So why is that? And the same thing is true about the other way around. Let's say my machine is decided by state by Tn time-bounded Turing machine. Now I have the Turing machine that goes to accepting state and rejecting state. Then I can build this Turing machine that prints 1 or 0. Basically, if I'm in accepting state, erase everything, print 1. If I'm in a rejecting state, erase everything, print 0. Now it's the older version of a Turing machine, basically. Huh? So what this lemma 1 and lemma 2 say, that these two definitions are the same, but they're also same in terms of time bounds. If the old machine was Tn time bounded, the new version of the machine also will be Tn plus some number time bounded. You will not get a quadratic blow up or something. So these two machines are equivalent not only in what they can do, but also how many steps they're taking. That's basically what we're saying. Because now we also care about how many steps we're taking. So lemma 1 says that you had the older, if you have an older decider, then you can build a decider with reject and accept states. And lemma 2 says if you had a reject and accept state decider, then you can build the older machine that writes 0 and 1. And you can see that there you need more time the other way around, because now if you go to accept state and reject state, it's not the one step that you're adding as you did in lemma 1. In lemma 2, you have to erase everything that is written, because there might be many things written on your tape, and you go to accept state. Now you have to erase everything, and then write 1. That's the difference, because you need to make more steps. That's why it says OTN here, and not just Tn plus O1. Think about it. You need more steps in lemma 2. That's why they're different. And okay, now that we define our complexity classes. So it's defined as set of languages, right? So time KTN is what? Time KTN, so Tn is a given function. So let's say think n squared or n squared plus 3 or something. So time KTN is set of all languages or problems, as we usually think about them, such that this language is accepted by deterministic. By the way, we have not discussed non-deterministic Turing machines, but I'm going to throw in the word deterministic here so that you know that there exist some different things that are non-deterministic. So, but for you, it's just a Turing machine now. The Turing machines we discussed are deterministic. So it's accepted by a OTN time-bounded k-tape Turing machine. So this is time KTN. Okay, so time KTN are just all languages that are accepted by OTN time-bounded k-tape Turing machine. So for example, let's just write just very easy example. So what would be like time 2n squared? This would be all languages that are accepted by two-tape Turing machine. So I can construct a two-tape Turing machine that accepts this language in O(n) squared time. O(n) squared means that it can be 3n squared, 4n squared plus 4, or 110 to the power 67 n squared plus 4. That also works. So if your two-tape machine makes less than any of this, because all of them are in O(n) squared, then this will be, their language will be in time 2n squared. Okay? And by the way, pay attention that I say that this language is accepted by this machine. But I know that accepted and decided will be the same for these two things, because this, if it's accepted by a time-bounded Turing machine, it has to halt. That means it's also decided. We'll see it in a moment, but let's just keep it as it is. Is this definition clear? And then time Tn without k here will be union over all k of such things. That means that this is actually a subset of time n squared. So time n squared means that it's accepted by some tape Turing machine in O(n) squared time. I do not care about the tapes. If I specify a number here that I'm asking for this two-tape machine or whatever. Actually, you should prove it. I don't care. So lemma 3 says that accepting and decided by time-bounded machines is the same, i.e., if L is in time Tn, that means there exists a Turing machine that accepts it in time Tn. This happens if and only if there is an OTN time-bounded Turing machine which decides L by state. So you tell me why. Exactly. So this is actually very easy. This point here just says that all the new definitions do not change the time constraints. And that's why you have to use OTN here, because when you go from old new definition to old definition, you pick up this O here because you have to erase things. So we always assume Tn plus OTN, you're saying, or what? Yeah, we always assume, we always assume this, because we have to read the whole input. But if you do not do things like this, then you have to do what you're saying. But we always assume Tn is bigger than n, because you have to at least take n steps to just read the input. We assume that our machines always read the input. But that's just an assumption, technical assumption. But here's a very important example that we will hopefully have enough time to cover. So let's say x is just some symbol which is not 0 or 1. And my language is like this. I have a string of zeros and ones of length n. Then I have x n times. And then I have again the same string. So let me. So it's like this, 1 0 1 0 1, for example, 1 2 3 1 2 3 4 5. Then I will have 1 2 3 4 5 1 0 1 0 1. So it has length 5. This has length 5. This has length 5. So it's the language that contains all such strings. When the length of this guy is the same of this guy and this guy for all n and for all strings. Okay? Now I'm claiming that this language is accepted on two-tape Turing machine in linear time. Can you tell me how to accept this language on 2 tapes in linear time. Or except is the same as this side. So I give you a string, and in linear time, in linear steps, you should tell me, you have 2 tapes now, in linear time you should tell me whether this string is of this form or not. So exactly what you're saying will work. So let's say you're reading such things. So you read 1, you copy it on the second tape. Read 0, copy on the second tape. Read 1, copy, copy, copy. So now you have 1, 0, 1, 0, 1 on the second tape. Now when you're reading X, you go back on the second tape. So you read 1, 2, 3, 4, 5. So you go exactly back, right? And now you again just compare if it's exactly the same thing, what you're reading, whatever you have it on the second tape. So what you just go through like this, and you just copy, go back, and read. And if everything is, if you find a mismatch or number of X's, then you reject. So as you said, so we can do it in linear time on 2 tapes. What about 1 tape now? Yeah, exactly. So you have to go back and forth like this. So you see 1. So if you only have 1 tape, you see 1. You start moving right until you read X, 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 X. After you read X's, and then you see something other than X again, and then you compare. Because you save it in your... So you read 1, save it in your state. You go all the way here, compare. Then you come back here, save 0, go back here. So the fact that you have to go back and forth, back and forth, back and forth picks you up a quadratic time. Now my question is, even though I know that L is in time t2n and L is in time 1n squared, how am I sure that L is not in time 1n? Even though you gave me a concrete Turing machine that does this, maybe there exists another much more clever algorithm. So Turing machine is basically an algorithm, right? So maybe there is a much more clever algorithm that does it on 1 tape in linear time. So it says nothing. Constructing, I know that this is here and this is here, okay? But it doesn't mean that this is not in a smaller subset. So what I'm saying basically is this. So you have all languages which are time on 1 tape n squared. But the things that are here, time on 1 tape n, are inside. Because if you're not making more than n steps, you're also not making more than n squared steps. So I know that my language is here, but how do I know that it's not here? I know that my language on 2 tapes, I can do it in linear time. So what about, can I do it on 1 tape in linear time? So these are the questions of complexity classes. And this is where the P comes in. So my first, which we actually showed this already, I want to recall where did we show this, is lemma number 4 says that time Tn is inside time 1 t squared of n. What this says that this is any tape Turing machine, right? Remember, time Tn is just any tape Turing machine, which doesn't make more than Tn steps. This says that if your algorithm works in Tn time on some 17 tape Turing machine, 27, whatever, K tape Turing machine, that it works on 1 tape Turing machine in quadratic time. This actually we showed. If you remember, I think if I go back to our slides, it will turn off the recording. So let's not do this, but let me just remind you that when we did the simulation theorem of K-tape machine with a 1 tape machine, remember we showed that if you have a K-tape machine, you can transform it to a 1 tape machine, and we did this blocks kind of thing. So when in one cell you write, I don't know what we called it. We didn't call it blocks. We called it what? Tracks, exactly. So when we did it in tracks, we also did the time analysis there, and we need. If you remember, if our K-tape machine was making t steps, then the simulation was making t squared plus something steps, some constant. So we were getting quadratic blowup because we were shifting things back and forth. This is exactly what it says. So it is shown in tape reduction theorem, so you can go back and look at it, that if you're using time tn on k-tape machine, in square amount of time, you can do it on one tape. So basically this here is automatic. You just simulate this two-tape machine on a one-tape machine and you will get the quadratic blowup. But it doesn't mean that you cannot do better. Okay, let's do the same exact thing with space complexity now. So this was steps we're making, and now we do the space. Space ksn, so Sn again is a function, let's n squared plus 4 or something. Space ksn is all languages that are accepted by a deterministic, again, just for you it's a Turing machine, in OSN space-bounded k-tape machine. So the only difference is the word time and space. Here we meant it's not making more than OTN steps. Now we mean it's not taking more than OSN, it's not visiting more than OSN cells. And exactly the same way we define space Cn is when I do not care of how many tapes am I using. Yeah, if you care about Sn is less than n, you can have that our input is on a separate tape and you never touch the input. You can see in some of the books they do this. So you have an input on a separate tape and you only count cells visited which are outside of the input. So we're not going to address this here. And again, in the simulation theorem that we did, where we used tracks, we showed that you're not really changing the space you're using. So whatever you're doing on k-tape Turing machine in Sn space, you can do it in one tape Turing machine on the same space, because you're not really using more space. So the space Sn is inside space 1 Sn. Exactly. You can think of it this way, or you can actually, so there's an equality here. So by definition, if you look at the definition here, where is our definition? I think we have a recording, yeah. Space Sn is just the union of all space 1, space 2, space 3. So all the languages that are accepted in one tape, two tape, three tape, any tape. So as this space 1 is inside space Sn, trivially. So you add tapes and do nothing. So don't think about this as something with many tapes. So basically let me just write it down. Space, let's say, I'll give you a concrete, so n cubed, let's say, is space 1 n cubed union space 2 n cubed union space 3 n cubed, god damn it, n cubed, and so on. So it's a union over all k. So if your language is in any one of this, that means it's accepted by, let's say, 3-tape Turing machine in n cubed time, it's in space n cubed. And clearly space 1 is inside here because it sits right here. And if space Sn is in space 1 because of the tape reduction theorem, then there's an equality here. So instead of talking about all k-tape machines for space, you can just talk about one tape machine. And now we come to a not so obvious theorem that, let's see if you have an idea how to proving. Remember, we just proved that accepting and deciding is the same if your machine was time bounded. Meaning, if your machine is time bounded, it halts, right? So accepting is the same as deciding because it can never loop. But now I'm saying it's the same thing with space. Accepting and decided by space-bounded machines is the same. This is not so obvious if you think about it. i.e., if your language is space bounded by function Sn, so it's not occupying more than Sn cells, it's not visiting more than Sn cells when accepting L, there is an OSN space bounded Turing machine which decides L, so tells you yes and no. So let's stop this for the next lecture and let's discuss in this. Unfortunately, yet again, we lost the last recording, so I'll try to next time pay closer attention to whether my media is saving or not. I think that is the issue, that in the final lecture I unplug things and it's not saved. But anyways, I will again have to do a quick rundown. So we were so the recording cut off here, I think, at lemma 6, that accepting and deciding is the same also for space-bounded Turing machines. And the idea, I think, that we had a lot of discussion in the class, and you guys actually came up with the correct idea to do this. Hence, I think skimming over this proof is not very damaging. So let's go into a proof. So accepting and deciding should be the same. So of course it was trivial to prove when you have a time-bounded Turing machine, right? So if your machine is time-bounded and it's accepting some language, then by definition it halts in some time, right? So whatever your time-bound is. So if it halts, then it's actually a decider. So there's not much to prove in time case, but what about the space case? So let's say I'm operating in a given space, and if I'm operating in a given space, the idea behind that you also actually contributed to is that if you give me space, let's say small s, then there are only finite amount of configuration my Turing machine can be in this space S. And if I make more than this number of steps, then there are configurations on this space. That means that on this space the configuration repeated, and if configuration repeats, since the Turing machine is deterministic, the next step is completely defined, then this means that the configuration repeats and my machine is looping, so I can detect this if I make more steps than possible on this space without configuration repeating, and I say that it loops and I reject, basically. That is the main idea. So let's look at the proof, right? So this direction is trivial, meaning if my machine decides this in space Sn, of course it also accepts it's in space Sn, because deciding is stronger than accepting, basically. It places a condition on strings that are not in the language, whereas accepting only places the conditions on strings that are in the language, so it's weaker. So now the most interesting part is the other way around. So let's say now I have, I'm realizing this idea here, what we had before. So let me give you a pen. So let's say S is some number. Let's for simplicity of drawing, S is 4. So, and then let's take this space 4 here. So this is my S, space S. So there are 4 cells here. So how many configurations can be on this cell, right? So let's just write a configuration. Let's say 1A00. So this is some alphabet, and then configuration means that I'm also in my state, let's say Z13. So this is a one concrete configuration. How many ways are there to configure this? So to write a configuration in space 4, right? First of all, how many strings can I write in space 4? So it depends on my alphabet, right? So if my alphabet is what? 0, 1, and in my case letter A also, like this. If this is my alphabet, then I can write 3 letters in the first cell, 3 letters in the second cell, 3 in the third cell, and 3 in the fourth cell, right? Because there are 3 alphabet letters. So in generality, this means that if there is sigma if this is my sigma, however many letters there are in sigma to the power S. This is how many strings there are on 4 cells. Now, okay, how many ways, how many places can my state be? So my head of the Turing machine be, it can be in 4 places. Here, 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 and here. All right. So there are as many
S many places for head. All right, and then how many states can this place now take? So let's say my Z is Z0, Z1 up to, I don't know, Z14. If there are only 14 states, that means they're also then for each of the configuration of the string and the place of the head, there's then there are again 15 many different ways Z can be. So because Z would be 15 here, right? So then there will be Z many ways this states basically. And this is what this is. So you take S, if I go to my laser pointer, so there are this many strings, this many states, and this many places of my head. So on space S, I can write this, I can have this many configurations. And by KS, I denote the number of configurations on space S. So KS is less, so this is the most amount of things. So this KS is less or equal to this. And count head position states, blah, blah, blah. And what is log K of S? Why do I calculate this? So if KS is a number, right? So it's a natural number. So if I want to write this natural number in binary, the length, the size of the string in binary will be log of K of S. So I want to write this down and count later. So log of K of S is log of S plus log of Z plus S times log of sigma, just applying log on both sides, and it's O of S. So linearly for S, I can write KS in binary. And now I'm constructing the my machine here, right? So I'm constructing my machine that will detect somehow whether my other machine, so L is in space Sn, right? So there exists a Turing machine that accepts this in space Sn. So I'm now constructing a new Turing machine that decides in space OSN, decides the same language. So my new Turing machine should look at the old Turing machine and somehow detect whether it accepts, rejects, or somehow if it loops, it should detect it that it loops because I mean, since it loops in a finite amount of space, it should detect that the configuration is repeating and then it should reject. This is the first step of constructing it. So the first step is to actually so what I have to decide is that my old machine is M, right? So M decides L, so M accepts L, right? So what I want to construct first is a machine, well, submachine. So my machine will have two parts. In the first part, I will decide whether M accepts W using a space S. So I'm given space S. So I'm just formalizing this proof, nothing really. So I fix space S, so it's a natural number. So let's say S is 27, I don't know. Some natural number I fixed, and I'm running my old machine on W, and I want to decide whether this accepting thing happens in 27 steps or not. How do I do this? So I take an input W and also takes the binary length of S. So I have to take S as an input because I have to decide whether M accepts W in space S. So I take S in binary. So I have to think how many spaces am I using for deciding it, so I don't go beyond this N, right? So what I do, I run M with W, and I'm also counting number sigma of cells visited, and in binary number of tau of steps made. So I'm running M on W, but I'm also counting so let's say on tape 2 or whatever, I'm counting how many cells this guy is visiting. I'm saving it in sigma, and I'm counting also how many steps this guy is taking. Now, if sigma is bigger than S, right, I will reject. Because what this first step is supposed to check whether M accepts W in space S. So if it uses more than space S, then I reject. So S is a given number and I reject. The second thing I do, I count whether tau, the steps this guy is making. So this sigma is cells visited, right? As it says, that cells visited. So now tau is steps it's made. So if its tau steps is bigger than ks, I reject again, because it never exceeds s, because if it exceeds s, I will halt from point 2. So if point 2 is passed and I'm counting this guy, I'm operating within space s, and if tau is bigger than ks, that means the configuration had to repeat, because there are ks many configurations at most. So if it's bigger than ks, so if it's bigger than this number, let's say, the configuration repeats on space s, and I know that this guy is looping now inside s, and I'll know that it will never halt, right? So I reject again. And now if none of this thing happens, and if the only other possibility, that is m accepts it's in space and time bound. Okay, so what does 1, 2, 3, and 4 do? 1, 2, 3, and 4 takes an input w and s and tells you whether this machine accepts this thing within s somehow. But it also takes into account the fact that if it's loops inside, that it's actually rejecting it. So it's kind of decides within s. So okay, let's first look how much space does this thing consume. It consumes space n because it has to read w, and then it has also since log of ks is less or equal to os by this guy here, writing down ks, and also, okay, sigma will never be bigger than s, right? Because as soon as sigma is bigger than s, I reject. But ks, the size of writing down ks, is also os. So, and binary s is also log of s. So at most, I will use n for input and os time to write down ks. So this whole thing uses n plus os time. Okay, now what? How do I actually decide for language L, right? So what I do is I run the above test for different s's, right? I do it for w equals n, because at least I consume size n, right? So I run it for w binary n. So first I will check, does this thing accept in size n? Then I will check, does this thing accept in n plus 1, n plus 2, and n plus 3? And I do this above test, and I do this, so I go from n to n plus 1 to n plus 2, if the above rejects because of 2. So if the size is exceeded, so if it rejects because of 3, if my first procedure rejects because of 3, then I know that this thing is not accepted, and it loops, and I put out reject. If it accepts, I put out yes. If it rejects, I put out no because of 3. But if it rejects because of 2, I increase s, and I try n plus 1. I try n plus 2. I try n plus 3 until I reach s of n. Well, not s of n completely, but I know that my machine is O s of n bounded, so there exists some function f, which is O of s of n, which actually bounds the space of this machine. So I do this n plus 1, n plus 2, until I go to f of n, right? So I do this until of f of n, and if until f of n, all of them got rejected because the space was exceeded, I reject because the space is exceeded. And if this succeeds at some point, for s of n, this uses space. So doing this thing, of course, uses the space n plus O s of n, and this will succeed for in this bound. All right, so I do this, and if this, so I build the decider basically, right? Because by exactly detecting that the looping happens by number 3 here, right? So. Okay, so basically what this proves is that so this succeeds in before we reach this Sn. So this Sn is Fn here. So I use the Fn for this because it's OSN. So there's some function here, and this process will succeed in Fn time, right? So it will take Fn plus O Fn, which is the same as OSN. OFN is same as OSN because F is in OSN. Okay, right? Because you will get yes and no answer in the end, so you will get the decider. So from now on, accepting and deciding will be the same because we only consider space and time-bounded Turing machines. All right, next, so our rundown is that. So yeah, this I said I will put it as an exercise, that what we proved here is that if you have a machine which is space-bounded, right? The space-bounded machine, let me get my laser pointer. So you have a space-bounded machine. We just proved that this is also time-bounded because it halts. If you have a space-bound, so let me restate it. So if I have a language that has a space-bounded Turing machine, right, which is accepted by a space-bounded Turing machine, then it is decided by a space-bounded Turing machine. And decided by a space-bounded Turing machine means that this machine is also time-bounded because it's a decider. It says yes and no. It halts always. So basically, if my language is in here, meaning there exists a space-bounded Turing machine, that means there exists a time-bounded Turing machine that decides this language. So this language is also in here in time, but exactly where? So how what is the bound of times? I know, okay, my language, there exists a Turing machine that is also time bounded if it's space bounded. Okay, what is exactly this machine here? We construct this machine, which is time-bounded machine, and what you have to do is actually count how many steps this machine is making. And you will see that this machine, the one that constructed here, is making exponential amount of time. Meaning that if your initial machine M was space-bounded within Sn, by OSN, then this machine that we constructed here will be time-bounded by 2 to the power some constant times Sn. And I actually wrote down the solution here, like a small tip yesterday. I was going to say this and cover this, but this I will leave it as an exercise to kind of check how many steps this machine is making time-wise, the time steps. But you will find that it's an exponential time here, and what this proves basically, so this time 2 to the power Cn, if you take over all constants, this is called exponential time. And what we proved here, if you take Sn linear, so in this case, if you take Sn equals n, what we proved here as a concrete case, that space, the linear space, is inside exponential time. So like x time is, instead of Sn, I take n here, and if you do this here on the same thing on the left side, you will get this. And on the first look, it seems like space is much more powerful, meaning if you're bounded by linear space, look what this guy is saying, if you're bounded by linear space, you are basically exploding into, you're still bounded in time, but bounded by exponential time. Okay, yeah, this is not really a rundown, I just redid the whole, too much in detail. So, okay, we covered this as well. Constant tape compression and constant speed up. So, let me record this a little later because I have to go now. Okay, let's do a really quick rundown of this proof as well, so you at least have the time to look at slides, and I will just emphasize the main points. So what we do is a theorem about constant time compression. What this explains is why did we use the big O's in all of this stuff, like here, time ktn, so is L accepted by deterministic OTN time-bounded machine, and why didn't we define for concrete function Tn? Why is there a big O necessary? The same thing for space, so why do we do this? The thing is, you cannot get rid of it, so why big O notation cannot be avoided. And what the idea is that if L is accepted by some function Sn tape-bounded Turing machine, so it does not exceed, the input of length n does not exceed space Sn, and you give me some constant number C, then I can construct a new Turing machine and accept the same language by Sn divided by C Turing-bounded machine. Look what this thing is saying. This thing is saying that you can reduce the space by factor of C as much as you like. For the same language, you just construct a new Turing machine which uses much less space, and plus some linear artifact here. And the idea here is very simple. What you do is you have an unlimited alphabet, so you can do this. So the idea is written out here. So if you have 6 bits, let's say 0, 1, 1, 0, 1, 1, like this written out, I can think of it as 2 bits. basically if you tell me reduce the space this bits occupied by factor of 3, what I will do is I will write them in 2 bits, 0, 1, 1, 0, 1, 1. So now it is 2 bits. And in this case, C, I took 3, I reduced this by factor of 3. But what I did before, if my alphabet was 0 and 1 only, now my alphabet contains all possible triples. In my triple, so if I had my 2 alphabet letters, 0 and 1, my new alphabet now contains 8 letters, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, and so on. So all possible triples. So the fact that I can do this, increase the number of the elements in my alphabet, keeping it finite, means that I can actually reduce the size of cells. And this is the artifacts of arbitrary size of the alphabet. And so let me quickly run down how I will actually implement this. So I can assume that I have one tape machine M that accepts L, and it uses space Sn. And I can assume it's a one tape because I know that if it's a K tape machine, I can go to a one tape machine without actually losing out on space. I did this in the slides before, so I assume it's a one tape machine, and what I do is I blow up my alphabet, so I can write tuples now. So before, if my alphabet was A, so my bits were, let's say, 0 and 1, and my C is 14 now, so I want to reduce the size of bits by 14. What I will do is I will take C 14 tuples of my alphabet. So if it was 0 and 1, I will have 14 tuples of zeros and 1. So it's 0, 0, 0, 0, 0, 14 times, and so on. So my new alphabet is still the old alphabet, so I can still write into just one symbol, but I also can write tuples now, C tuples, and I will reduce the whole alphabet. And how I do this is I partition tape M into blocks of C tape cells each, like I did this, like I had 6 bits here, now I have 3 and 3, so C is 3 in this case. And if my input would occupy n bits, now it occupies n divided by C bits. So it occupied 237 bits, now it occupies 237 divided by, if my C is 10, let's say I would have 23.7, and I have to round it up, so it will occupy 24 bits at most. So this compression will work in space n plus 1 or n plus 2, because like how would you compress? You have to read the input, let's say 237 cells, it will take 237 cells, and while reading it, so once you read 10 cells, you read erase, read erase, read erase, read erase, you read 10 cells, erase all of them, and on a 10th cell you write them as just one block of ones and zeros, right? So you compress them, but you have to go to the blank on the right and overshoot. And if you want to make it regular when you're coming back, so if you want to sit on the first cell, then you have to come back and overshoot once again, so it will be n plus 2 or something. Find the endpoints, so it's n plus 1, n plus 2, whatever for overshooting. And now you can simulate the same machine. So now, so if your machine was, let's say, erasing 0 here and moving right, erasing 0, writing 1 and moving right, then you simulate the same thing here. You just erase the whole thing and just write 1, 1, 1, right? And that's it. So you just simulate however this machine was operating here, exactly the same way, but now you operate on blocks and you take n divided by C many blocks. So your blocks now Cn divided by C and n plus 2 for the compression that you got. That's it. That's in very short. And it turns out you can also do the similar thing for the time compression. But in time compression, let's say again, so if L is accepted by Tn time-bounded Turing machine and you give me a number, then I can construct a new Turing machine that takes 4 divided by C, 4Tn divided by C. So if C is large, this 4 doesn't really matter. So what this really thing is saying that you can simulate C steps of an old machine with 4 steps of the new machine, basically. So I will so let me erase this again. So I will what I will do is, so I will have the new machine, and this new machine makes 4 steps instead of making c steps of the old machine. That means that tn steps will be tn divided by c steps will be simulated. Well, tn steps will be simulated by 4 times tn divided by c steps. So let me do this how and this is for the compression again. So again, what I do is I replace tape alphabet a of m by this thing, A union AC, but 0, 1. So what does this 0, C do? Let me just give you an example, maybe write it down. So let's say you had let's say you had 6 things, 1, 2, 3, 4, 5, 6. You have 0, 1, 1, 1, 0, 1. So, and let's say I want to compress it against these 3. So what I will do, so I will compress it in 2 things. I will have 0, 1, 1 and again 1, 0, 1 as I did it for now. I'm in 2 cells here, but then I will also, let's say initially if my machine was here, I will write 1 and I will write in green, I will write 0. What this 1 and 0 stand for is just the location of the head. This 1 means, this 1 here means that head is on cell 1, and what 0 means that there is no head here. So I'm also memorizing where the head is standing here because I want to then simulate the steps here. So for example, if my head moves somewhere here, then I will still have 0, 1, 1, but here I will write 3. So from number from 0 to C, I'll write here, and this is supposed to remember where the head is located. So 0, 1, 1 with head standing here is a different in this cell from 0, 1, 1 with head here. By the way, this is a green line, but there's no line here. I mean, this is just a single cell, and this is just again a single cell here. But somehow I remember where my head is located. So my new alphabet has to be an old alphabet, C tuples, and the less number from 0 to C that remembers where the head position is. So again, a block of M of length C and a head position within block 0 means that there's no head. And again, we partition tape M into blocks of C tape cell each. And first, again, I do the compression. I compress W into length N divided by C. But let's count how many steps do I need for this. By the way, my machine is now K-tape because I cannot go to the 1-tape machine. Otherwise, I will get a quadratic blow up, which I do not want. So I keep it at K-tapes. So let's say on tape 2 then, what I do is I copy input and compress to tape 2 and erase tape 1. So I'm reading, I have to read n many bits in the input and maybe overshoot it left and right for blanks. So it's something like n plus 2. And I also now write it in blocks on tape 2 and I erase tape 1. Then I move head on tape 2 to the start of the compression input. Now on tape 2, my input is n divided by C because it's now compressed. And again, overshooting on blanks, it's plus 2. So it takes n plus a divided by C rounded up plus 2. And from now on, I exchange roles of tape 1 and tape 2. So now I compressed my input and it took what? It took m divided by C plus n plus 4. So it took this part is for compression here. And now the simulation process. The simulation is that I can, what the crucial point is that the C steps that the old machine is making, it can only change 2 blocks, one to the left or one to the right. So for example here, so let's say again I have like 1, 2, 3, 4, 5, so I have 6, 3 and 3, and let's say I compress them like this. So I have 0, 1, 1, 1, 1, 0, and let's say instead of a number I indicate here is my head, right? Then let's say in 3 steps, so here C is 3, right? In 3 steps, the most thing this guy can do is go 1, so it will go first step here, my pen is, second step here, and maybe then it will come back here. The third step is again here, so it went boom, boom, and boom, like this. And then it modifies something, so maybe it wrote 0 here, maybe it wrote 0 here, and then it just wrote 0, the 1 again here. So it modifies 2 blocks. So it's obvious that if I'm making C steps and C is the size of the block, I can at most modify 2 blocks, 1 block to the left and 1 block to the right. And if the old machine was doing this, the new machine has to emulate the same thing. So it's the new machine is looking at this block here, right? So it has to read the whole block, memorize it in state, see what is going. So if my old machine was moving right, it has to go to the right, read the state, also see what's happening here, because it really depends, right? If there was 1 here, then maybe something else would happen when it comes back. If it's 0 here, then maybe something else would happen. So really, if I have to emulate C steps of an old machine, I have to read this tape, go memorize it, read this step, memorize it, change it, and change it. So it takes 4 steps. That's the idea. So can model C steps of M by 4 steps of a transition function operating on blocks rather than things. And since 1 step takes 4, then since C steps take 4, then 1 step takes 4 divided by C. So T steps take 4 T time divided by C. And what are exactly these 4 steps is I read the current block, I memorize it in my state, meaning that I change the state according to the specific block. Then if block left, so in C steps, so if I exit this block, so I go to 1 block to the left or 1 block to the right, I also have to read the neighboring block, because what happens afterwards really depends on what was in the neighboring block. So I read current block, I read the neighboring block, also change the states accordingly to this, so I know exactly what block 1 and block 2 are happening. Now I have to determine these 2 blocks after C steps. So I have to see what the old delta is doing and update the current block and update the old block. So memorize, read 1, read 2, update 1, update 2. So it's 4 steps. So in these 4 steps, I simulate C steps. So in this case, 1, 2, 3 steps. I will do it in read, update, update. So four steps. So as I'm doing C steps in 4 steps, that means I'm doing 1 step in. So if I divide both sides by C, basically, so C steps is equivalent to 4 steps. That means 1 step is equal to 4 divided by C steps. So T steps is equivalent to 4T divided by C steps. So basically that's what it is. That's where the 4T divided by C comes from. And sorry for this quick rundown again, because we didn't have enough time to. Well, I lost the recording. Yeah, we did spend a lot of time on this, but you can stare at the slides, and we'll start with universal Turing machines next.